I'd like to welcome you to this meeting of the Healthy Planet Action Coalition with Sev Clark, Australian inventor who's developed the technologies of nanobubbles and buoyant flakes. And Sev will explain these technologies and their synergies to us for albedo restoration and a range of other climate repair benefits. So, Sev, I'll invite you to say a bit more to introduce yourself and get underway, and look forward to your presentation. Thank you.
Thanks, Robbie. Good day to you all. Unlike most presentations, I'll give you time to digest what is on the next screen, and Robbie will be handling the slides before I comment on it. A summary of the method's implications, followed by a Q&A session, will attempt to answer your questions and provide for your input at the end of my talk. I begin by making the seemingly outrageous claim that you could do something with global effect by simply forwarding the recording link of this to your contacts who might be interested. Such is the power of our messages going viral. Next slide, please. Brightening our darkening planet, or at least the oceans and clouds covering most of it, is the key. What we would like to do is to regain the 2% albedo loss we have suffered from the loss of marine cloud, ice and biomass. To brighten the ocean's surface so that it develops a lighter, perhaps turquoise shade from that of Homer's wine-dark sea, and becomes cooling and aerated with tiny nanobubbles, as well as sequestering safely in the depths carbon. Let's try for Quico Toro's idea of 1% brighter, then see if more is needed. I propose that we could do this safely using the combination of flake-nutriated marine microalgae, phytoplankton, reflective nanobubbles, and the marine cloud thickening at gated scales, locations and intensities. The combination of enhancing the cooling effects of albedo, the reflectiveness of phytoplankton, bubbles and clouds would be accompanied by the co-benefits of increasing biodiversity, improving fish stocks, de-acidifying surface waters, and of sequestering carbon. Modelling and practice will inform us how best to deploy these methods, taking into consideration other methods then being tried. This isn't the only solution by any means. And it will also allow us to develop early and reasonable forms of governance, of improving cost, equity, and community acceptance. Learning by doing, in other words. Next slide, please. I'm giving you 15 seconds to digest this because it's a fairly complex slide. The pink and purple ocean areas showing nutrient deficiency, substantially overlap. This makes treating them all the easier. You'll note that iron in particular is less deficient bordering continental land masses. Hence, we should not aim to fertilise these, as they may already be suffering from too much runoff nutrient. The method proposed, the ultra-slow release of buoyant flakes, should be effective, scalable, fast, and of low risk and cost. Next slide, please, Robbie. "20 seconds for this. The nutrient sources to be used are all sustainable, as they are waste products from other large industries. Their use is representative of a circular ecological economy, if you like, an eco-economy or eco-squared economy. The iron comes from the red mud left over from alumina extraction. The phosphate and trace elements come from the phosphatic clay wastes left over from what can economically be extracted from rock phosphate. And the opaline silica is a substantial fraction of the rice husks left over from rice milling. The binding hot melt lignin glue powder is left over from treating straw with the organosolve process that liberates its sugars, which may be used in precision fermentation and for other purposes. Regarding equipment, the bog carrier vessels used to gather the flake materials, then disseminate the finished flakes annually over ocean areas, could be obsolete vessels superseded by larger, more economical ones. Next slide, please, Robbie. The activities of diazotrophs, particularly the symbiont ones living inside diatoms, means that they can make their nitrate nutrient from dissolved nitrogen and sunlight on an on-demand basis, with no waste. When consumed up the food chain, this provides the higher levels, including ourselves, with protein. I've also recently learnt that some phytoplankton can control their buoyancy by one of several means: by increasing or decreasing the volume of free gas, of low-density lipids, of organic solutes, carbohydrate reduction, water, biosilicification, or changing the iron concentration inside their cells. Also, by clumping together or by swimming using their flagella, for those which have them. For large diatoms, buoyancy change can be particularly effective at vertical movement because they are less affected by seawater's viscosity or maybe Brownian movement than our smaller species. This also means that they can access deeper nutrients in the ocean. Next slide, please, Robbie. "12 seconds for this. Note how the dark blue of the originally nutrient-poor surface waters is brightened when either wind-blown dust, volcanic eruption, upwelling, buoyant flakes, or continental runoff provide phytoplankton with the needed nutrients. Whilst the ocean brightening we envisage occurring over most of the ocean may not be as bright as green grass, it should still provide enough cooling to reverse global warming over a couple of decades. Next slide, please, Rory. 15 seconds for this. Different ocean regions will require different optimal proportions of mineral nutrient. The acronym FEPSI, think Pepsi Cola, is an easy way of recalling what are the key nutrients to be added in most cases. The 10,600 figure is taken from the logarithmic mean of the extended Redfield ratio for iron in diatoms, iron to carbon in diatoms. It provides us with a huge lever for regenerating ocean biomass and biodiversity. Next slide, please, Robbie. "12 seconds. Note what is focused on by the 3 magnifying glasses in grey. They are the albedo enhancements provided by surface bubbles in seawater, spume if you like, or in our case, nanobubbles, by micro and macro algae, and by the white marine cloud nucleated by oxidizing DMS emissions from those same phytoplankton. Next slide, please, Robbie. 20 seconds for this. Note that SIDS, small island developing states, could be particularly advantaged because of their large EEZ, their exclusive economic zone waters. This is just because they are amongst the most threatened and impoverished peoples. The prospective timeliness of buoyant flake development, manufacture, deployment and monitoring is particularly important, as it may avoid us passing through too many more tipping points. Next slide, please, Robbie. This is good news. In fact, it is bubblingly good news. Next slide. "15 seconds for this. This photo is taken from the Anzai Kantestu, sorry about the pronunciation, YouTube video showing nanobubbles being produced at 8 meters depth, where they were successfully used to revive degraded parts of Tokyo Bay. The slight diminution in reflectiveness of the nanobubble stream as it moves away from the source is probably caused in part by the 5-degree dispersive widening of the jet, but more to the 20% oxygen lost from the bubbles to the surrounding water, in which it dissolves rapidly. Assuming that the protective shells forming around each nanobubble increase its life from around about 5 minutes to around about 4 months, this is a beneficial factor of some 35,000. The protection is due to several factors, including because the bubbles themselves become surrounded by gas-saturated water and therefore doesn't allow more gas to be saturated into it, by ionic layers which act as shields, by the static negative charge, electric charge, that forms on tiny bubbles which keeps them from coalescing, and from the neutral buoyancy of the composite bubble particles in the sea surface micro layer, means that the bubbles are not exposed to the atmosphere, so they cannot burst. Next slide, please, Robbie. 12 seconds. Ocean currents of different velocities would carry the nanobubbles for up to thousands of kilometres in 4 months. Much slower Gaia currents might only carry them for tens to hundreds of kilometres. The actual cooling effect will need to be modelled for each gated deployment after parameters have been established. My guess is that the cooling from local to regional to global extent might range from a negative forcing of 2 to up to 7 watts per square metre, though possibly much more for dense bubble plus flake plumes. Next slide, please, Robbie. 15 seconds. Notionally, applying the double-barrel method of buoyant flakes and nanobubbles regionally might be sufficient to protect the Great Barrier Reef from further coral bleaching, and a few such regional applications might cool the entire Gulf Stream and prevent excessive ocean heat from entering the Arctic Ocean. Applied from multiple partial clock hands within a great ocean Gaia, it could be enough to brighten, cool and regenerate ocean biomass there. Ocean biomass which we haven't seen since the early days of whale fishing 3 centuries ago. Next slide, please, Robbie. 12 seconds. No scale has been attributed to this design, as experiments are needed to establish the optimal dimensions. If pressed, I would say that toroidal units of a diameter of 3 to 7 metres might include the optimal size, whilst strings of anchored units linking wind turbines by power lines, or indeed radiating from isolated turbines, might be of lengths ranging from 0.4 to 4 kilometres. Note, my variant of Anzai's system that uses spinning disc-shaped diffusers is likely to be substantially more energy efficient than are methods that involve pumping immense volumes of seawater at speed in order to optimise the size and remove the emerging bubbles from the diffuser surface. What possibly intermittent energy that is required would be substantially reduced because of the lubricating effect of the bubbles on the spinning discs. Next slide, please, Robbie. Ten seconds. Likely outcomes include the long-lived, months-long, surfactant-stabilised sea surface nanobubbles, combined with the sometimes milky green of the underlying phytoplankton, serve to brighten, cool and aerate the ocean, as well as ameliorating extreme weather events. A second effect is that ultra-slowly released FEPC buoyant flake nutrients and diazotrophs, which fix the nitrogen, should allow rich and stable ecologies of marine life to establish themselves throughout all remote oceans. And the final likely outcome I propose is that both humanity and the biosphere should benefit from the regeneration of lost marine life, albedo, and biodiversity. Next slide, please, Robbie. Let me summarise the implications of the talk so far. To opponents of active methods to save the biosphere, I would say, please recognise that all current strategies, from denial to active measures, are failing. Put aside phantasmic fears and concentrate on real identified problems. Try something new. Try greening and brightening the ocean. The next slide, please, Robbie, will give you some useful links, and I thank you for your attention. Our host will now take up the Q&A session. That was just a little extra slide which I put in, but go back to the previous one.
Thanks very much, Sev. That's a very comprehensive and clear explanation from my perspective, and there's certainly some questions that I would have, but I'd invite everyone to raise their hands, and I'll call on people in order to ask questions, starting with Jonathan Cole.
Hi, can you hear me okay?
Yep.
Great. That was a great presentation. Two quick questions. One is, you use the word leavened, like leavening. It seemed to imply some sort of baked goods, but I probably misunderstood it. And then the other one is, what is the rice husks currently used for on land, I guess?
Right. No, you were quite right. Leavened is right. The leavening occurs to give the composite flakes buoyancy, which the rice husks alone don't have in sufficiency. So what the leavening agent is actually common garden urea, which is used as a fertiliser on fields. And urea has the nice property of degrading into two gases when it's heated to temperatures which are about the same as those which soften lignin, so it becomes a glue, 170 degrees Celsius. So in fact, the leavening process is a bit like some breakfast cereals you will have seen, which are they're expanded with a bit of gas inside them, and once they cool down, that carbon dioxide and ammonia gas stays in them until it's released by the slowly degrading flakes. Rice husks have very few uses. They're used a bit for animal bedding, but as 130 million tonnes of them are produced every year, that's an awful lot of animal bedding. They are sometimes used as a fuel, but they're a horrible fuel because the silica inside them coax the furnaces and clogs them up, and they don't have much value anyway. People have tried to find other useful methods for them. A few are emerging, but basically it is a waste product. And if we can take 100 million tonnes of that 130 million tonnes waste product and turn it into nutrients, particularly for diatoms in the oceans, that's a really good use of it.
Thank you.
Greg?
Thank you. Yeah, thanks for the presentation. It's great. So you have 5 tests underway right now. I'm wondering the scale of those tests, and if assuming that the outcomes are positive of those tests, what is the next stage in toward deployment of this?
Right. The tests have been done by one or other of these 5 international labs, 2 of which are from the global south, by the way. They vary from simple bottle tests in a lab to carboy tests to mesocosm tests in the ocean. There have been no tests using my formulation of buoyant flakes at scale, and there should not be until the lab tests have shown that everything is safe and controllable. The funding for these is running out, and the labs are looking around for more funding to establish their highly prospective early results. They're expected to be some pre-publication papers put out possibly this year, but we really want to have a lot more independent groups going around the world and testing it out in their waters at small scale and then gated up to see that it works for them. And we hope to learn from all of these to learn by doing, so we can get the best positive outcome and minimise any possible adverse effects.
Thanks. John?
Yeah, thanks, Sev. That was great. I really think this is a winning combination. Putting the nanobubbles and the buoyant flakes together. I love the buoyant flakes, but the combination is terrific. My question is more about the nanobubbles. But what size are you looking at the moment? And wondering whether, I know the microbubbles don't have a very long life. They sort of rise quickly and they're very reflective, though. Whereas nanobubbles do stay suspended for longer, but they're not as reflective. So I'm wondering whether there's a combination of the two that is the best of both worlds. To reduce the coalescence using nanobubbles and surface tension, and yet extend the life of the microbubbles. So, what size you're looking at the moment?
Yeah. In fact, bubbles of all sizes have about the same reflectivity. They've got that silvery look which you see of bubbles in a glass of wine or champagne. What we're looking at is if the bubbles are generated several centimetres underneath the ocean, we want them to be sufficiently buoyant that they can just rise to the sea surface microwave in that small area. And to make them rise, they need to be around about 5 micrometers in diameter. Now, those 5, as they rise, they'll lose gas, and they'll probably become closer to a single micron or nanobubbles in size. So the idea is to so calibrate the diffusers and the air pressure going into them and the spinning rate of the discs that we produce pretty much uniform 5 micron diameter bubbles several centimetres underneath the ocean. And those will then rise up enough to the surface and then stay around there for months on end, hopefully being taken by ocean currents away to where they can do most good.
Yeah, as usual, it comes back to the nozzle, doesn't it? And if we get the right nozzle, that'd be the way to do it.
But Anzai Contestu does seem to have got the right nozzle. He's got the material for the nozzles he uses is a mixture of carbon and carbon fibre, I think, and ceramics, and those two things are very good because they're they tend to be hydrophilic, and therefore they're not going to be reduced by water coating the inside of the pores. So it should be a whole lot more efficient, and we can adjust the spinning rate and the gas pressure so that it becomes optimal for that area and ocean temperature.
Yeah, yeah. There's a bit of tuning involved. Yeah, that's right.
Yeah.
Yeah, that's good. We're thinking along similar lines. That's good. It's great work. But, having that biosurfactant is the key. We don't want chemical surfactants. We don't want to put chemicals in the ocean. It's got to be natural, and that's where the algae is perfect.
Yes.
Yeah. Good stuff. Yeah.
Good.
I'll let others speak. I could talk further, but I'll let others speak. Okay.
Sorry, Dennis?
Sure. Thank you, Sev. I'd like to focus on the economics of these techniques and their application, the fixed costs and the running costs, say, per 100 square kilometers of ocean area treated. Starting off with the the rice husks, there, as you say, are something like 130 million tons of rice husks produced in the world, but they are a bulky material that would be sourced from an extremely widely dispersed set of locations around, particularly South and Southeast Asia. And so you have a major logistical problem in actually, purchasing, bringing them, trucking them to a location, then the cost of treatment, and then the cost of distributing in the ocean. Have you done some economics on the rice husk challenge? It's a very, very significant challenge when you think of the material, where it's produced, how it's produced, and how it's currently distributed.
Yes, I have. You'll find it on the NOAC website, buried in amongst the 30 or so other things. What I guess will happen is that many of the rice mills are on rivers, and you can, once the rice has been separated from the husk, as you say, is very bulky and very light. So what I'm proposing is that you get rice water, the water left over from boiling rice, which is a very low-level glue, if you like, clag we call it in Australia. You would spray the rice husks with that, put them through a heated roller, so they're sort of canoe-shaped, a hollow canoe-shaped shape is flattened, so they become flattened flakes, and the density is increased possibly threefold. You would then take them down the river, probably by barge or something like that, to a seaport nearby, and then that seaport, which may or may not have a flake factory on it, could be then, you would transport them using pneumatics, so simply blowing the thing through tubes to fill the holds or to empty the holds, and you take them to the place where the rice factory was, when you'd bring together the minerals and the glues and make and bake your flakes. The input materials are, well, some of them actually the mining companies will pay you to remove, because that they have to maintain them in these expensive and toxic tailings ponds. And if they can sell, if they can get rid of the stuff, they don't have to do that. And we're also then prevented from the normal mining disasters of things which are not properly maintained.
Mm-hmm. So then with all of that, have you worked out some of the economics of what it would cost for a given area of ocean to be treated with the flakes?
I haven't worked it out for a given area. In the main paper, I've worked out how much of each nutrient would be deliverable per year to a square kilometre of ocean space, and I think it's about 95 kilograms of iron would be distributed over a square kilometre, which I think is quite a substantial amount of iron given the 10,600 factor. It's not nearly so good for the phosphate and silica. We're probably not going to be able to make all the oceans completely sufficient in those with the sources I'm proposing. But if iron and nitrogen from the diazotrophs can be provided at scale, and then the other two nutrients will tend to accumulate over time, whales will tend to recycle them, and hopefully will begin to build up to a less nutrient efficient ocean system itself.
Mm-hmm. 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 Thank you.
Yeah.
Okay, my question. I think this is great, Sev. I like the vision of turning the ocean from dark blue to light green is one that really resonates. I'd be interested in your comment on the carbon dioxide removal potential, so the carbon sink sequestration ability. Also, how does this whole combination of nanobubbles and buoyant flakes compare to marine cloud brightening? Because effectively what you're doing is, instead of pushing salt aerosols through a nozzle, you're pushing air, and air is a lot easier to work with than salt water in terms of generating tiny particles that will exhibit the Toomey effect of, the smaller particle, the higher the reflectivity. So yeah, let's go with those for now.
Yeah, taking your second observation first, you're absolutely right. Both a mist droplet and a nanobubble have comparable reflectivity, but while the mist particle might last a few days as a cloud, a nanobubble can last up to 6 months and probably averages out at about 4 months. So you're getting a huge extra benefit of the nanobubbles over the mist particles. You're also correct in saying that it ought to be more energy efficient to generate a nanobubble in the surface water than a mist particle up 1,000 meters. So there should be, MCB is great, but I think the bubbles are possibly better. And of course, you also do get an MCB effect from the phytoplankton. So you're using both. You're both creating more marine cloud and you're making the surface more reflective. Coming to the CDR side of things, this is a matter of some contention amongst the scientific fraternity and sorority. Scientists are now beginning to realise that organisms which vertically migrate daily or seasonally have a major effect on carbon sequestration. Not only would krill, which eat phytoplankton in the surface, sink down to the darker depths during daytime, but at those darker depths they would excrete and breathe out much of the carbon they've taken in from the surface waters, which of course allows more carbon dioxide to be dissolved in them. And you'd still have the marine snow effect of the phytoplankton and zooplankton, you would have in the great ocean gyres, those ones which are downwelling ones. If you fertilise the area above them with buoyant flakes, then a lot of those phytoplankton would be carried down with the downwelling water, and the downwelling water goes pretty much to the ocean basins and benthic depths. So those gyres might be particularly useful places to make CDR happen.
Thanks. Okay, further question. How do you assess the political resistance, notably the London Protocol definition of ocean fertilisation as dumping of waste?
The London Protocol allows scientific experimentation. Once scientific experiments had shown that it was a benign and effective method at small scale, the London Protocol and Convention does allow for nation states to increase the size and monitor results as they do so. And one of the benefits of the method is that such monitoring can be done transparently to anyone in the world who's got access to a computer terminal, because the PACE satellites put up now can show how areas of ocean surface brighten, and they're also good enough to say just what species of phytoplankton are growing there at that time, and therefore they can say these species, say large diatoms, have a very good CDR effect. So no nation, no rogue nation or rogue entrepreneur will be able to get away without the results of what they've been doing being available and seen by all. And if they're doing naughty things, then they can be suitably enforced not to, and
So
quickly.
it reminds me of the Green Revolution in agriculture in the 1960s, increasing cereal yields. And it's a green revolution for the oceans. Norman Borlaug was the great scientist who championed the Green Revolution. And it occurs to me that the fishing industry should pay to fertilise the oceans because it would significantly enhance their sustainability and yield.
Yes, but they'd need to have the rights for the harvesting of fish from the areas they nutriated. They'd need to be given exclusive rights. Now that's a little bit difficult because the plume of flakes moves with the wind, and so there would need to be independent observation of which area had been sufficiently fertilised by this corporation or nation state to say, okay, you can have that range right, if you like, for the next 12 months, but then your nutrification is ended and you lose those rights. So if you want to keep on doing it, you need to take a new area.
And then there's the public good dimension of restored albedo and carbon dioxide removal, which should be funded by states as a much more effective climate strategy than emission reduction.
Exactly.
Thanks very much, Sev. Mike?
Nice. Nice. I guess I want to follow up a little bit on what Dennis was saying about infrastructure. Dennis was looking upstream. I want to sort of look downstream. You had a note in there that you had to get 1 particle per liter. I'm curious why you said per liter. Is it to be at the surface, or are you talking about assuming that through some through the mix layer or something like that.
No, I didn't say this. The scientists determined in their labs that they wanted to try a concentration of 1 flake per litre in their bottles. That's where that comes from. I would be saying I want to spread flakes at a rate which will give the nutrient deficient areas of the ocean 95 kilograms of iron per annum extra fertilization. That's what I'm looking at.
Over what area?
Over probably about 80% of the global ocean eventually.
But sorry.
So I took let's say each ship is going along, spraying over 100 meters wide area.
Call it a kilometre wide, because you'll be using the wind and 2 large booms.
Well, really, that maybe, and everything. Well, and if you're getting a concentration, that means it's sort of going down through the mix layer too, which would sort of will up things a little bit. And you have it going at 20 kilometers an hour, sort of going along. You come out with on each ship running a couple of 100 days a year, you come out with sort of a couple thousand ships or something having to do this, it seems, which is quite a large infrastructure to try and make this happen if you're going to do it, and that's sort of for 1 passing per year or something like that, if I'm correct. It just seems
you're right. The scale, the potential scale is very substantial, but even 1,000 ships, and I haven't done the calculation, is only 10% of the global fleet. So it's conceivable, but and particularly if you're using older ships which no longer have a useful life, and you may well be able to do them with very few in the way of crews, and if you can, we fertilise most of our croplands typically once every year or two, sometimes more than that. Why can't we do the same thing for the oceans, but much more sparsely and much more efficiently using ocean-going vessels?
Well, I mean, it just seems a large investment. The nice thing about doing it on food is you get a product that you then sell, and so you have some money to pay for what you're doing. It's
we
sort
can
of
sell the fish. Nation states can sell their fish.
Okay, so you also have to capture the fish. Okay. So then I want to get to this issue of the amount of reflected light you have to get to. So right now, with the planetary albedo at roughly 30%, about 25 of that 30%, I think, comes from the clouds. And I think about 5% comes from the surface. The surface is a little brighter, so maybe 3% of the radiation going out is from the surface, the bright land, lighter surface. So 2% is from the open ocean that you can see that isn't covered by clouds, but you have to do the whole ocean because that changes with time.
Yep.
So to get an additional 1% from the surface, you basically have to double the albedo of the ocean, or raise it by 50%, I guess. It's get it from 2 to 3.
Well, you raise it from 6% to maybe 12%.
No, well, I've got a little problem because only sort of less than half the radiation is visible radiation that I reflect, unless I'm somehow reflecting the infrared radiation that's coming in. But so I've got to essentially 50% or 100% increase the albedo of the whole ocean surface, I think, that's a really large change or something to try and imagine and make happen. I mean, it's interesting idea, and maybe there's some areas of the ocean that are mostly not covered by clouds where you can concentrate something, but it is a pretty big change in what the ocean reflectivity has to be. Is that right?
We've lost 2% of global albedo in the last several decades. What we would aim to do initially is to regain part or all of that 2%. Then we'd take a breather and say, do we want to go more? So we would start, you start small. You test how effective it is, you test how much it's going to cost, and you test how much extra benefit or revenues you're going to get from the other effects. Yeah, it is large, but it needs to be large. We're talking about trying to reverse global warming. That's a major effort for humanity, but I don't believe it's an unachievable benefit, unachievable size. You're taking it'll be a whole new set of industries, but industries many of which will be profitable ones. So, it might be the equivalent of the iron ore industry currently. We have giant iron ore carriers going across the sea and that. But that's if that means we can avoid going up to 2 degrees Celsius, it's very much worthwhile doing.
Yeah, well, so, I mean, to some extent, you're talking about solving or addressing the marine protein problem or the protein problem for the world. I mean, it's really interesting and important for that as an aspect of it. I'm just asking about this effort. It's so hard to really do it, change albedo by doing it at the surface as opposed to trying to get a smaller fraction in the clouds, which is why marine cloud brightening is sort of so interesting. I mean, they're basically talking about getting a relatively smaller percentage of change of what the clouds are.
The good part about the flakes is that we can basically make it it needn't be regional. We can have ships going in tracks which cover a small part of the global ocean over an entire year, and that means that with dispersal and that sort of things, that the whole ocean surface itself isn't increased a huge amount in one area and not at all in others. It's all slightly increased across the whole global ocean, and therefore the trans effects are likely to be minimized. You're not going to have huge regional effects in any place. You'll just have a marginal effect across most of the ocean, and that seems a whole lot safer way of doing things than having just doing a bit of MCB in a given area where it's propitious.
And on your bubbler devices, how much of an area would they generate bubbles for over a year?
Depends how fast the current is where you're doing it. In the Gulf Stream, it would go for thousands of kilometres. In a gyre, it might only go for hundreds of kilometres. So you'd need to have more installations in the slower areas, but they would also give more bubbles, more intensity bubbles.
Do they stay in the same place? Is that the idea? And then
no. You'd want them to be dispersed as much as possible. So putting them in where there's surface ocean currents is a good way of doing that.
Well, yeah, so they'd accumulate just like the plastics do in the gyres and things like that. You'd have to relocate them or something, I guess.
You shouldn't have to relocate the issuing. You'd have the bubble aerators would be fixed in the ocean, but you'd want to have more of them where the currents weren't so fast.
Oh, okay. They're fixed. The bubble aerators are fixed in the ocean. I
Yeah.
see. Okay. Thank you.
Oh, good.
Can I go ahead?
Robert Tulip, you're muted.
Oh, I'm sorry, I was speaking while I was muted. I was just saying that we're coming back for a second round of comments and questions, and I'd just like to check if anybody who hasn't spoken would like to chip in at this point before we go back to Greg. Okay, Greg.
I do have some questions. I'm not sure how I make the little hand appear in my screen. How do you do that?
I thought that might be the case, so that's why I'm coming around with this second method. So please, Bob, go ahead.
Okay. Very good, Sev. It's very interesting. It's something I hadn't really thought about before, the idea of nanobubbles, which I think I heard you say that 5 micron was typical. Is that right?
They'd start out as 5 micron, but they shrink because they lose gas to the water.
Okay. All right. And these bubbles can last for like 4 months?
Yes.
That's a surprise to me, but that's fine. I can be surprised.
Yeah, lab experiments have got it up to 6 months, but I'm saying no. Let's go for 4.
Okay. A question, and forgive me, I just haven't. This is the first that I'm hearing about this. Exactly what do the rice flakes do for the bubbles?
The rice husks nutriate phytoplankton.
Yes.
And when phytoplankton die, they emit dimethyl sulfide, which helps
Yes.
Yes. Cloud formation and things like that.
Yes.
And more in particular, the surfactants which they emit, along with the DMS, that is, they coat the nanobubbles. They form a protective coating around a nanobubble, a bit like a cell wall does. A cell wall is made out of very similar things to surfactants, and they stabilize the nanobubbles, so they last not just minutes, but for months.
So the surfactant shell, that's how you get the bubbles lasting for months.
Yes.
Okay. And is it primarily diatoms doing this?
No, it's all phytoplankton life in the ocean emits some kind of surfactants, particularly when they die. And I haven't studied about which is most efficient, but because they all do it, we can use whatever marine biomass is there is going to emit these surfactants.
Oh, when you refer to large diatoms, how large?
Diatoms have got a wide range in size. I think the larger ones get up to around about 10 or 15 microns in diameter, but you'd need to go and check out the literature.
Okay. All right. As far as the energy to operate these aerators, you show power cables and so forth. What energy source would you envision?
Offshore floating wind turbines anchored.
Okay.
So we could use existing wind farms, particularly when they are producing more power than what is required by nearby industry. So we might say, okay, when the wind's blowing strongly, you're producing too much power, we'll take that extra power and we'll make bubbles from it.
So you would be then operating most of this equipment fairly close to shore then?
No, can be right in the mid-ocean.
Oh,
But
okay.
in mid-ocean, you're not going to get wind farms because they're too far away. So, yes, the wind farms are typically reasonably close to shore, although some in the North Sea are quite far out. But you would also be having some of the wind turbines deployed specifically to make just nanobubbles, nothing else.
Yeah, okay. Is there any utility for these new micronuclear energy that float on
Could be.
ocean barges?
Modular nucleus could be, but yeah. I have a preference for using wind power for this. But yeah, it could easily be.
Okay, all right. I think that's about all I have for now, though I would like to start thinking a lot more about this and talk with you individually in the future, if that's on.
That's certainly on. Go to the NOAC website, which is on that last slide I had Robert put up, and you'll see there are about 30 different unpublished papers on the Buoyant flakes and 5 or 6 on the nanobubbles.
Okay.
Yeah, we'll put the link in the chat. I'll put the link to that website in the chat. Okay. Thanks very much. Now I'm going to jump to Ron before we go for the second round, and keep it short, Ron.
Thank you, Robert. And hi, Sev.
Hi.
I want to just follow up the more general question that is, kind of following up on some of the earlier comments. And we had this discussion quite extensively when we did the paper, the HPAC cooling paper, and it related to, what scale this particular effect could have in terms of cooling. And we ended up settling, as you recall, that this could potentially have local to regional cooling effect, but because of the difficulty, the time and resources that would take to actually scale this up to a very large scale, it would very unlikely that this could, be used to actually provide global cooling, at least in the next 20 years or 25 years.
That was your opinion, not mine.
Okay. So I wanted, and I was, of course, anyway. So I have to say, anyway, I relied quite extensively on Mike, of course.
Yeah.
It seems reasonable to me. I mean, so it seems to me, and that's what I sort of wanted to question you about. Would you be comfortable? I mean, I think it seems much more reasonable because you're also talking about multiple potential co-benefits. And so what this seems to be is a kind of a more specialized niche application that could be quite useful, as you say, for the Great Barrier Reef, for enhancing fishing fertilization in various parts of the ocean. I mean, I would see it as a more of that kind of a targeted niche kind of method that could be very helpful in many ways, for all kinds of other applications besides cooling, and might include a little bit of cooling as well. But we've had this discussion, in many contexts within HPAC, is that, when you do the cooling on the surface, in land or in ocean or whatever, it just does not have the kind of efficient scale of impact as when you do it higher up, in the clouds or particularly the stratosphere, of course.
Ron,
It could be useful for local areas, but but it's hard to see how this would. So I'm just, it sounds like you are still,
Look,
you
great
still have
point,
some
Rob.
reservations about the conclusion we had in the paper.
Okay, thank you.
I was like, yeah.
Okay. Yes, it would start off with niche applications. That's the way to do it. And you'd hope the niche applications would be widely scattered by widely different parties, so you could get the information necessary to show the optimal effect. However, once those niche operations were generating revenues for small island states, for instance, you're going to fairly rapidly find that global industry is going to say, hey, we want a part of this, and we want to do it at bigger scale, and we want to do it in our area or in the South Pacific or the wherever. And so if it works in the niche, okay, let's expand it a little bit more and see if it works wider. You're not going to want to have ships going down into the Antarctic waters in wintertime, but maybe you can have them going down in summertime, spreading the flakes and letting them slowly release their nutrients over the next year. You probably don't want to have too many wind turbines operating in oceans where they're giant icebergs moving around and destroying them, but go a little bit further towards the equator, you'll be able to have them there without the danger of them being destroyed by a giant iceberg moving. So, yeah, it'll grow as human ingenuity and our climate needs require it. Is my opinion.
Thanks. Okay, let's go back to Greg. We've got 20 minutes to go, so we've got 4 people, so we'll have roughly 5 minutes each, unless there's more people put up their hands. Thank you. Greg.
Okay, thanks. So I'll rattle off about 3 questions, and you can answer any or none. This is sort of a follow-on to Ron's, perhaps, but assuming good outcomes from the tests, things go the way you believe they will from your studies, and assuming you can get permission from the powers that be, what would be the most sort of optimistic, aggressive scenario for a rate of increase of albedo as a function of time? Because I mean, I look at it as it really is a crisis. We want to do things on a time scale shorter than 20 years, actually, not longer, although most people think in terms of 20 to 50 years to do squat. What would that be? Second, why are your papers you got 30 papers unpublished, why are they unpublished? And then third is, are you getting any press at all in the popular press? Because as Bob Fry says, I never heard of this, and I never heard of this before I started coming here. And I've never heard it in New York Times or anything like that, actually, at all. Maybe it's occurred occasionally. But so those are 3 things I'm asking. You can answer any of them or whatever.
If the early experimentation and early trials go well, we should be able to expand it rapidly enough to have most of the global ocean covered by 2040 to 2045, 15 to 20 years. We've got the ships, we've got the mineral and the rice husk resources. What we don't have are the permission and the flake factories to actually produce these things at scale. Now, a flake factory is going to be something like the same technology as what it takes to make breakfast cereals. The technology is, I could notionally make them in my domestic oven. They wouldn't be as good or as economically, but it's that level of simplicity. You're throwing 4 or 5 ingredients together. You rolling them around a bit, and then you're baking them, and that's it. Regarding the publication, I do not have a doctorate in anything. I've got a science degree in chemistry and a bit of other things, and I've got an MBA from Stanford University. Those are not strong academic qualifications. I don't have a university backing me. I've got only my own funds, which are negligible. You can't get published in academic papers except if you have someone like Ron and Mike who can give you some credibility, and thank you both for doing that. That's why the papers are unpublished. However, if you look at Quico Toro's 1% Brighter blogs, if you look at Paul Gamble's work from Nori, if you look at some of the other stuff, they are beginning to get into some level of public recognition. What was I'm trying to remember what the third.
You sort of answered. It was a matter of it's never appearing in the press, and you're saying it's dribbling in gradually from the niche level. But like you see occasional articles in the big papers, Times, whatever's on cooling techniques and geoengineering. I've never heard them list this. Bubbles or the flakes. And they talk about ocean iron fertilization occasionally. It's never made it that far up, and it was just a curiosity that you can't get it even a mention in these sort of generic geoengineering things. That was sort of it.
The scientific paper Nature has recently come out saying we need to have cooling. That's a major advance. We know that Jim Hansen is now saying something similar. Say that we're with the warming in the pipeline, the only way to handle it is by some methods of solar radiation management. So it's the pendulum's beginning to shift. Whether it shifts fast enough will be in part up to us.
Look, I'll jump in because I think the really intriguing thing here is the combination of innovative technologies, and it's something that's entirely new. And human psychology is relatively averse to new things, and we also see a context of extreme political suspicion towards geoengineering, and so there are quite reasonable reasons why this has not had a wider dissemination. But I'd like to ask Sev you to comment on two things. Firstly, the potential for the Great Barrier Reef to protect against coral bleaching, and secondly, the comparison to other methods of disseminating iron. I think one of the key things about the rice flake idea is that they float, and so they don't sink, whereas some other iron methods are more likely to sink.
In one of the slides, it's got a picture of the ocean currents around the world. One of those comes from the east towards the Great Barrier Reef and then splits, half going north up the coast, half going down the coast. If you were to put buoyant flakes and nanobubble generator, there, go back, the left-hand half of that. If you see where I've got the aerator generator and the flake plumes in the right-hand side of that blue part of the diagram, that's showing how the nanobubbles and the flakes could disseminate right over the entire barrier reef and indeed much further south. OIF is being studied by a number of groups, including a crowd called EXOIS, and these 5 research institutes who I've been working with, and I'm a member of the Marine Biomass Regeneration Consortium. That's led by Cambridge, but also has University of Southern California, Cape Town University, the Indian National Institute of Oceanography, and the University of Hawaii involved in it. They're hoping to bring in the University of the South Pacific in Fiji into that fairly soon, but they are at the moment hampered by having run out of funds, even though their early research showed really good results.
Thanks. Now, Dennis had his hand up, but he's put his hand down. Did you still want to speak, Dennis?
Well, my question was just answered by Sev. I was interested in the groups that were doing collaborative research on this, and particularly, as you mentioned, it was good to hear that the Woods Hole XOIS group you mentioned is working on this, which I think would be very significant. They're quite a large group of scientific organizations, and that could give this a real boost. And then, of course, we will be having Russ George talking further with us, and I think that he may be interested in integrating this into his approach. And then you have Peter Fikowski, who's doing a major experiment on OIF, ocean iron fertilization, in the Philippines, and he might be interested in deploying this on an experimental basis as well.
So Russ will be joining us in 4 weeks' time. So for our first presentation in October.
Next. Yeah. So that's all for me.
Dennis,
Robert.
could I ask? Sorry to jump in again. Do you see the international agricultural research organisations as having potential? Like I'm thinking IRRI or the fisheries, or there's a range of agricultural research bodies, and I mean John Dixon could also comment on this.
That's a very interesting. I hadn't really thought about that, but of course, the International Rice Research Institute may be interested in this because they have been working for many years on how do you use rice husks effectively. So indeed, Sev, we could follow up on making contacts with IRRI and then with other CG centers as well. Over to you, John, for your thoughts on this.
I'm just absolutely fascinating. But I think in relation to that last question of Rob's, that the World Fish Organization in Penang, who works quite closely with IRRI on a number of quite successful projects, they're primarily focused on more coastal environments at the moment, Sev, but they have in the past, of course, worked with deeper ocean resources too. But definitely, if there's any trouble getting hold of those contacts, either Dennis or I could very easily help. I know a previous Director General of World Fish, and Dennis is right next door to IRRI.
Right. Well, then, John, why don't you follow up with World Fish, and I will initiate contacts with IRRI, and maybe we could set up a call for Sev and key individuals at the Rice Institute to have a chat about this.
And show them give them the URL to this session we're having.
Exactly. Yeah. Perfect. Once the URL is out, I'll send it to a few of our colleagues at the Rice Institute, which is right next door to where I live, as John mentioned.
Excellent, because I've really wondered why is it that the international agricultural research institutions haven't engaged more on albedo as a key constraint to agricultural productivity.
primarily, actually, Rob, because they haven't been funded even at a seed funding level to step into that space.
Exactly. Yeah, but
Yeah.
Dennis?
But I think it's ignorance also, although many of them work on various issues related to climate change, and there's a whole global program on climate change solutions. I think albedo enhancement is, something that, like the vast majority of researchers around the world, are unaware of what we know about albedo enhancement. So I think there's another issue for us. John, you and I talk frequently. Let's work out a strategy for the CGIAR to get engaged in this.
By the way, I think that in terms of the CG, of course, World Fish and area worth following up on, but I think the climate program was actually more generously funded and had rather innovative leadership for for many years. So I think that might be an interesting space to step towards. They are, of course, focused on research, but piloting exercises such as this, Seb, could certainly be part of their strategies, and they too, of course, have very widespread networks that do connect to industry. So I think that might offer opportunities.
Well, it's great that we've got Dennis and John, who have such deep career connections with CGIAR, which is the Consultative Group for International Agricultural Research, which brings together researchers on many fields, including Dennis's work on agroforestry, and John's done extensive work on the economics of agriculture and related topics. So that's a really good lead, which Sev can follow up. Let's hear from John McDonald.
Yes, just quickly, Rob, that another co-benefit, Sev, is the impact on microplastics. There's possibly a case that the iron will oxidize and catalyze the microplastics to help to destroy microplastics in the ocean. So, and it may, in fact, also increase the specific gravity of the microplastic and cause them to sink and be sequestered as well. So I'm talking to a university about carrying out a simple experiment to test this at the moment, but it's just another co-benefit possible.
I hadn't appreciated that possibility.
Yep. Add it to the list.
Good one. All right. Well, we've got 5 minutes before our scheduled completion. I'd encourage Brian, if you're listening, to comment on what you've heard from the conversation. I know you weren't here from the start, but we've had discussions with Sev and about this before. But what's your thought?
Well, I think anything that can restore nutrients to the epipelagic zone of the subtropical oceans is desirable. And, I think we're going to need all the methods at our disposal to rebrighten our planet, particularly in the tropics and the subtropics, where, as Alan Gadian puts it, that's where most of the heat is absorbed, and that heat works its way towards the poles. So I think, the notion of rebrightening our planet begins in the tropics and subtropics, and Sev's approaches seem to provide one of several ways that we can work to rebrighten the subtropical regions. Thanks.
Very good. I'm going to take the opportunity of sharing a file that I just made. If I can just, sorry. Here we are. This data from Peter Cox of Exeter University, analysing the SARAS data. I've added this trend line onto it to show how the collapse of albedo is accelerating, and so how back in 2001 albedo was sitting at around 99.8, and by 2023 it had collapsed to 97.3 watts per square meter. So it's the reverse. When you've got this accelerating trend, it's a feedback that the forcing seems to be for it to continue to increase. So it just illustrates the urgency of methods such as nanobubbles that can put a stop to this quite dangerous trend.
Beautiful graph, Robert. Very useful.
Rob, would you mind sharing that graph with us?
Yeah,
too?
well, I embedded it in the AI attachment that I sent to HPAC yesterday, but I'll send it as a standalone post.
Yeah, terrific. It's relevant too to this group. Yeah.
Okay, well, we've got 2 minutes to go, so I'll just invite Sev to provide some final comments, please.
Well, first of all, thank you all who participated. I delight in hearing challenges and working out answers to them. It's a matter for whether our little group can get out some of these ideas so they become ones to be considered by the scientific and decision-making groups in the world, because from what we can see, there are no other answers. Brightening is the key answer to addressing global warming and giving us time for the other necessary methods of carbon, of greenhouse gas removal and of emissions reduction to take effect. But those are not going to take effect for decades. We need something which can be done by 2040, 2045, and which will be effective. And I'm sorry to say that this seems to be the only combination which can have major effect. We'll be able to do great things with forest evapotranspiration and with biochar and with changing our agricultural practices and indeed possibly our diets. But all those take a lot more time and effort than it would be to simply scatter some flakes across the oceans and add some aeration to the oceans as we do with our normal aquarium tanks to make them healthier. So let's hope we can do something with this, and let's hope that our little seed can grow to something which can look after our grandkids. Many thanks all.
Thank you very much, Sev. I think it's a really brilliant presentation, and I look forward to further discussion, and hopefully we'll get the investment and the interest and the engagement to see rapid testing and deployment. So thank you all very much for coming along, and we look forward to sharing the recording of today and continuing discussion.